Yes. Thanks, Luca, for that fantastic introduction. That was great. So I want to talk to you today about building the next generation of compute primitive in Rust. And I'm going to be talking through a bunch of stuff, but let me start by introducing myself. I'm Luca. I'm a software engineer at the Deno company, where we build Deno. And I'll explain to you a little bit about what Deno is in just a minute. I've previously led our cloud compute team, Deno Deploy team. I now mostly work on special projects like our database. And I do a lot of standards work in the JavaScript space. So I work with people at Whatwig and W3C on things like the HTML specification or like fetching data in browsers, kind of things that you interact with a lot. I'm also on TC39, which is the standards body that actually makes the JavaScript language. Yeah, that's terrible, but anyway. I chair Winter CG, which is a community group at the W3C to make server-side JavaScript runtimes more interoperable with each other. So what is Deno? Deno is a next-generation JavaScript runtime created by the guy that originally wrote Node, because unlike the Rust ecosystem, the JavaScript ecosystem is pretty terrible. I don't know how many of you have used JavaScript. Like, raise your hand if you've had to use JavaScript before. Okay, so you know what I'm talking about, right? Like, there's no linters, there's no formatters. It's just like you Wild West, right? You type things into an HTML file and hope something usable comes out the other side. But really, like, there's no single standard library like there is in Rust. There's no standard formatters, linters, testing frameworks, package managers. Everybody uses their own, uses some wild concoction of different ones together. And this is terrible. My boss is Ryan Dahl, the person that originally wrote Node, who's responsible for all of this. And then he decided, like, 4 or 5 years ago that, like, he was fed up with being responsible for this, so he's going to go fix it. So we're building Deno now, which is sort of an all-in-one toolbox for developing web apps. And I'll give you a quick demo of what it is. So, oh no, my editor just turned dark. This is the problem when you have it set up to like auto dim based on things. Okay, so this is just regular JavaScript. Actually, this is not JavaScript. This is TypeScript. I can write TypeScript files in Deno because plain JavaScript is pretty terrible, right? You have no types, you have no idea what's going on, and I don't have to tell you all this, you're all Rust developers. Developing without types is like, I don't know, you just don't want to do it. So yeah, we have types built in. I can log things out. I can run this, Deno run main.ts, and you can see it logs something out, great. But also we expose a bunch of IO things. So in a browser, if you want to fetch some data, you use like the fetch API, right? Which allows you to make HTTP requests. Deno implements that same API, so I can go fetch https example.com and I get the body out of that, so response.text, and you can see this is all async IO because we want to have like high concurrency. Yeah, so you see that actually nothing happened. It asked me, hey, do I want to actually allow read access to example.com? And this is sort of the first little trick that Deno has up its sleeve, which is we don't just give you access to the system as is. Deno is a secure sandbox, just like the browser, where you can execute untrusted code. And unless you explicitly grant read access or network access or write access, we won't really do anything. So it's asked me here, hey, do I want to allow access to example.com? I'm going to say yes. It goes and fetches the file and prints it out, right? Whew, internet was working. Okay, fantastic. But there's also some APIs that are not standard that we implement. So we, for example, have a way to read things from disk. So let's say I want to read some text from disk. I have this Deno global where I can read text file. And you can see there's like auto-completion, right? This is type JavaScript. This is not terrible JavaScript. I'm going to read out my EDC password file. Those are safe nowadays, right? There's no passwords in them. Print that out, and you're going to see again, it's going to ask me. I can bypass this. I can say like allow read EDC password. Oh, I misspelled EDC. Aha. Okay, so if you can type, it works correctly, and you can see it prints out EDC password file. Hopefully nothing incriminating in there. That's Deno. There's a bunch of tooling built in, like for example, we have a formatter. Deno FMT formats your code. We have a linter built in, so if I do something fun like comparing to nan values, which is returns false in JavaScript, actually returns false in Rust too, so don't blame JavaScript for this. But when you run the linter, it tells you this is bad, don't do this. So yeah, have a bunch of that kind of stuff built in. If I run out Deno help here, we can go through the subcommands real quick. Obviously, you can run code, have a built-in benchmarker, a type checker. We can compile single executable binaries. We have tooling to do coverage reporting, documentation generation, formatting, linting. We have a Jupyter notebook integration that lets you sort of write little notebooks for things. We're directly built into your editor through an LSP. We have a test runner, a task runner. We can self-upgrade. We can vendor your dependencies, whatever, right? We can do everything. So that's Deno. We love Rust. Deno is completely written in Rust. We maintain over 500,000 lines of Rust across our organization on GitHub. About 70 to 80% of that is open source. It actually took me a while to figure out how much code we had in Rust because apparently it's not very easy to get a line count just out of GitHub if you have like 180 repositories. But hey, I managed. We publish many crates to crates.io ourselves. For example, we maintain the bindings from Rust to V8. We have safe bindings to V8, which is C++. I'll talk more about that in a second. URL pattern to do URL routing, super fast WebSocket implementation, a text parsing library called Monch, Acme 2 client. You can see this is like sort of all over the place. Rust TLS Tokyo stream. And we help maintain various other things like Rust URL is something that I help work on, and probably all of you depend on Rust URL, right? And WGPU, which people who do GPU related things in Rust may know. A colleague of mine helps out on that. But yeah, we're not entirely written in Rust, actually. We use a little bit of C++. Actually, we use over 1 million lines of C++ in the form of Google's V8, which is a JavaScript virtual machine that is the thing that powers JavaScript in Chrome. Is actually the same thing that powers JavaScript in Node also. But we provide like safe idiomatic Rust bindings to V8. And you may ask now, like, why don't we write our own JavaScript engine? And that's a great question, but I think it's answered by the same answer as why does Rust use LLVM as a compiler backend, right? Because writing your own compiler backend for dynamic language or static language is just a lot of work, and you're not going to get that much benefit out of it. V8 is the sandbox that runs probably the most unsecure code in the world every day by a number of lines of code. And it's very highly audited. There's still obviously security vulnerabilities, but they're dealt with very well by a very professional team at Google. So yeah. Yeah, and then for Rust things, we rely on like the very excellent Tokyo. Thank you very much for Tokyo. It's fantastic. And Hyper to do HTTP, various other libraries obviously also. So yeah, why do we use Rust? Well, many other sort of things in this space that are JavaScript sort of related but can't be written in JavaScript for obvious reasons are written in C++. And C++ is, okay, I'm not going to say anything. C++ is a language, right? And you probably don't want to use it for new things. But yeah, so we initially tried using Go. This went about as well as you might have expected, right? Go's a great language for writing async HTTP servers, but it does not have the same reliability or strictness or customizability or performance that languages like Rust or even C++ for that matter do. And we needed something that was like really strict, that let us write code that was going to be reliable when executing untrusted code, when executing code from many different tenants. Something that was super lightweight for us to do like very lightweight virtualization with. Something that was very performant because, hey, if you're already using a language that is not known for its like dramatically fantastic speed, you don't want to make it even slower by like making your host side of that slow too. And we needed something that was customizable enough for us to plug in like V8 or other sort of complicated dependencies like that that don't necessarily integrate seamlessly with the Rust ecosystem. Rust provided us this. So there's a lot of really awesome things in Rust that make it very well suited for use cases like this. For example, like Rust's options and result and ADT enum types enforces a way of exhaustive error handling that is like close to none in any other languages, right? Like you have to really deal with your errors correctly. And you can use like anyhow to sort of just bubble up your errors all the way to the top. But if you don't do this, if you take a little bit of care, you can write really, really reliable code in Rust. That is sort of checked by the compiler to make sure that it's really, there's no edge cases that you've missed. Yeah, the explicit memory management obviously makes performance very great due to the way that you can sort of see whether code will be performant or not just based on the way it is written. If you have a clone in there, this is going to cause an allocation. If you don't have a clone, no allocation, right? This is transparent performance. And the board checker then enforces that it's correct, which is great. You can pretty easily integrate with C++, which for us was a prerequisite because we needed to integrate with V8. And you don't have like hidden runtime overhead of using garbage collectors or implicit atomics like you would with, for example, Go. And actually, like, fun story, if you try to like have two garbage collectors in the same process, we used to have like the Go garbage collector and the V8 garbage collector in the same process, things, very, very fun things happen. Like garbage collectors don't know that like I'm gonna go garbage collect now because the process is idle. And then it decides it's going to garbage collect. And then the other garbage collector thinks, oh, the process is now not idle anymore. I can't do my garbage collection. And then they like sort of ping pong between each other. Yeah, Rust also has like absolutely incredible built-in tooling. And I think for people that use Rust a lot, this is sort of boring at this point because we just know, like, I don't know, Cargo has Clippy and Cargo has a formatter built in. But if you're coming from ecosystems that don't have this, it's absolutely astonishing, right? Like everybody uses the same lint rules, the same formatter, the same testing framework, and the same documentation generator. Like, what? It's insane. Like, go look for another programming language that is like this, right? This barely exists. Go is something that is sort of close, but I don't think it's at the same level. Swift can't even agree like whether they should do formatting at all, like let alone what formatter to use. So back to Deno, what are we actually building? We're not just building a runtime and sort of the surrounding tooling for that, but we're really a cloud company. We want you to be able to write code that like looks very simple, is very simple, and then seamlessly deploy it to the cloud and have it just work there. Have it scale, have it be performant. And to do this, we use a compute primitive called isolates. And I'll talk a little bit about what isolates are in a second, but the way we think about this is that it's sort of the next frontier of cloud computing after containers. They allow very easy global distribution, very quick deployment, very little configuration, very easily virtualization. So I'm gonna give you a quick demo of that too. So I have our sort of management dashboard pulled up here. I'm already signed in. I'm gonna click on this new playground button. And I haven't prepared anything. So everything you're gonna see is live. Let's hope the internet's gonna cooperate. Okay, so it's popped me into an editor here, playground. This is exactly the same code I could write locally, just writing it in the browser now. I have an HTTP server here that takes in a request, returns a response object, returns hello world, right? You can all go to this URL right now. This is live. It just created this. It's running in like 35 regions across the world right now. And if somebody from the US would visit this, there would be like a little message down here that says, oh, it started code in the US. Let's modify this to see that I'm not cheating. Right, so I can change code and this works. But sort of the nice thing about Deno is that there's a bunch of batteries built in. So if I want to like do something with a database now, guess what? Deno has a built-in database. Deno.openkv. It's going to open a database. And let me modify this code a little bit. What I'm going to do is I'm going to add a view counter to see how many people visit my site. So I'm going to do kv.atomic to create an atomic transaction. And I'm going to sum the counter key by 1. So I'm incrementing it by 1. Commit that. And then let me get a result here. So kv.get. I'm going to get the counter. Oh. OK, there we go. Get the counter key. And let's return this. Return new. OK, typing on stage, not fun. There we go. Okay, so I've written 3 lines. Is there anything that I've missed here? No. Where? Yes, yeah, 1n. N is a big int in JavaScript, so like bigger than an integer. Oh, ha ha ha. Yes, thank you. Sorry? Yeah, refresh again. I missed an await. Yeah, so we have a counter, and as we refresh this, and I see you are all already actively visiting this, it works. Fantastic. Well done, everyone. So 3 lines of code, and I've added a database to my app, right? This is the kind of thing we're going for. What makes this possible? A new primitive in cloud computing called isolates. So let's go a little bit through the history of cloud computing. We started out with bare metal. Most of you are familiar with bare metal machines because you develop on them every day, where you have to install your own OS, you have to deal with security updates for your OS, to then install some sort of runtime or runtime libraries, like maybe you need OpenSSL installed, and then you can execute your code or your executable. The lead time here is very long, right? You're talking about a matter of weeks to get a server created, shipped to your data center, and installed. If you already have one, it's days to set one up. You have this upfront investment of hardware. On-prem VMs make this slightly better. You still have to wait around for your machines quite long, but once they're there, it's great. You can install things on them much quicker. There's a little bit of isolation, so applications can't really interfere with each other. Then came along EC2, and we had cloud VMs where you could deploy the same sort of VMs where you had like much more capabilities to sort of package things exactly like you wanted, but without the sort of upfront hardware investment. You could like instantly deploy things, and you were now billed not based on the number of data or servers you bought from Dell, but based on the amount of time that you're using one vCPU with 8 gigs of RAM from AWS, right? And it's important to note here that you're billed based on the sort of hardware that is allocated to you, not the hardware that you're using, right? So if you rent one vCPU from AWS and you're only using that at 50% utilization, you're still paying for one vCPU. Next thing that came along was containers, where now the operating system was sort of managed by someone else. You didn't have to deal with that anymore. You only had to ship the runtime with all of the dependencies you needed and the code itself. Still build on real time. And then the next thing that comes up is isolates. And isolates is a way for you to really give us just the code, and then we provide the runtime and all the dependencies. So this is things like WebAssembly or JavaScript isolates, right? Running in sort of sandboxed environments where we spawn the runtime for you. And there's a couple of benefits to this. For example, it allows us to have much higher utilization and support something called scale to zero, which let me talk about that next. So what are cold starts? Cold starts are a byproduct of a feature that many people use nowadays called scale to zero, which means that if you are hosting a server and you're not receiving any traffic to that server, you scale the app down, right? You shut down the app because what's the point of running it if there's nobody that's using it? But this does mean the first request to that app then has to start the service back up. This time is the cold start. This results from the work that you have to perform to sort of set up all of your like dependencies, your runtime, your code, your database connections that is specific to you as the tenant that like needs to be cold started. And this means the more work that you have to do, the longer your cold start. And one way of like reducing the cold start is by reducing the amount of different work that you have to do per tenant. Because if, for example, everybody uses the same version of OpenSSL, you can just preload OpenSSL for all tenants before you know which tenant is going to use OpenSSL. This means lower cold starts, less work to do specific to a tenant. And if you sort of compare this across different primitives, you can see like the more stuff you have to do, obviously, the longer it takes, right? If you have to start up a server that has like 30 hard drives attached to it, they all need to run their smart checks. It takes a long time. You then boot up an OS that is faster, but you still need to run like a DHCP handshake and do various other things. Boot up a runtime, load a bunch of code into memory, and maybe set up some like read-only heap or something. And then if you're talking about an isolate, you're really just executing code because everything else was already done beforehand. And you can sort of see this on this graph too. For VMs, you're booting up a machine, and that's the only thing you can do up front because after that, everything is different for every tenant, right? You have a different version of Ubuntu. Maybe somebody's using Windows. You can't make that assumption, so you have to wait until you know what tenant you're booting for to be able to actually start the kernel, initialize the network stack, and so on. With containers, it's slightly better. You do know exactly what version of Linux they're using because you're providing that version of Linux, but you still need to go boot up and configure their runtime, download their version of OpenSSL that they need, and so forth and so on, right? And isolates, again, make this better because there's less work that you have to do that's specific to a tenant. So the next part of this is utilization, which is how well can you make use of the underlying hardware resources? If you have a server that has one CPU, you want to make sure that that is utilized as much as possible across the day, right? If you have a server that's booted up that's consuming power, that is not being utilized, this is just wasting money. So you don't want this. And the way that big cloud vendors usually deal with this is that they just bill you by what they allocate to you rather than what you use. So if you want to have one vCPU available, you pay for one vCPU availability. And if you use only half vCPU, doesn't matter, you're still paying for one vCPU. There's another way you can pay, which is based by CPU time. So based by the amount of time that you're actually having the CPU do work, where the amount of time that the CPU is like spinning and doing something, right? And this means that for work that is very intensive, like image processing, you're going to pay more than work that is very simple, like adding two numbers, right? So you're only paying for the resources that are used. But this does mean that for the person that is providing you these resources, they now need to deal with having a really high utilization, because if they have a really bad utilization, they're not going to be able to cover their costs. If there's like 3 people on a machine, and in total they use like 1% utilization, and I'm still having to pay someone else for my whole 1 vCPU, I'm not making money. So achieving the sort of good billing, the billing that's good for the user, means that there's more work that has to be put in by sort of the host. And achieving this high utilization means that you need to achieve something called high packing density, which is the amount of tenants that you can pack into your underlying physical resources. And high density requires that sort of tenants are very lightweight. If you want to be able to pack 10,000 tenants into a machine that has 8 gigs of RAM, like they can't each use 1 gig of RAM. It's just math, right? It doesn't work. Which means that the best way of achieving this is that you let these tenants share resources with each other. So if they're all loading OpenSSL, I keep going back to this example, but it's easy, right? They all load OpenSSL, and they all load the same version of OpenSSL. Actually, that only has to be stored in memory once, because it's like read-only. The kernel can sort of deal with everybody seeing their own version of OpenSSL, even though it's all backed by the same bit of memory. Yeah. So the lower your baseline sort of memory and CPU consumption is, the higher you can have a packing density, which means the better billing you can give to your users. And comparing these baselines across different sort of architectures here is, if you have a VM, you need to boot up an operating system. This uses a bunch of memory, setting up like all the tables you need to track processes, open files, that kind of stuff. With containers, there's a bunch less you have to do because everybody uses the same operating system. And with an isolate, again, there's even less because you can now share things like OpenSSL or even the runtime between tenants. So this is another way to visualize this. If you have 4 containers that all use different versions of V8, they're all going to need different code sections that like have the sort of these are all ELF binaries, right? So they have text sections and code sections. They're all going to need different code sections because they're all built from different versions of V8. They may have different sort of static content in them, but there's one bit of difference between all of them, which is the actual code that they're executing, so the user heap. And if you're using isolates, you can combine all of this sort of static data into one, and the only thing that's different between processes then, or isolates, is this user heap. This helps you reduce memory usage. So yeah, we're not just building a runtime. We're also building a multi-tenant runtime hypervisor that runs these isolates in the cloud. We're building load balancers that lets you like globally distribute things in nice ways. We're building a control plane API server that lets you manage all of this. So like I went to the dashboard page earlier. There's an API that powers that, and that API is written in Rust. And we're building databases, like a distributed database that powers this Deno KV feature, for example. And these all have very different requirements to maybe the pure runtime, right? Like hypervisors require that the hypervisor itself has very low overhead because you're going to be running this on hundreds or thousands of machines. And like, if you can squeeze 5 more tenants into every one of those machines, that's great. You want to sort of minimize the amount of baseline overhead that the hypervisor uses up on each machine. You need to also have really high failure tolerance. Like if you're running a machine with 10,000 tenants on it and one of them crashes, and that somehow causes all of the other 9,999 to crash, you have a really, really bad time. Like, you do not want this. Trust me. So yeah, you need to be able to deal with errors incredibly well. HTTP load balancers are pure cost. You just want them to be fast, have as few of them as possible to serve the workload that you need. But you also want to have very predictable performance. You want to make sure that if you're in a scenario where you can't scale up fast enough to handle demand, you're serving traffic for users that are already connected to your system before you serve new traffic, right? So you need to be able to prioritize work well. And then control plane servers, you need to be able to robustly deal with inputs from users, like say that's parsing HTTP, parsing JSON, parsing protobufs. You need to be able to do that in a way without that then causing your system to panic and result in like denial of service attacks. And you need to be able to nicely return errors to your users so you can help them debug things if they've made a mistake calling your API, for example. And then finally, if you're building a SaaS nowadays, you need to do billing and you need to do email sending and all these kinds of third-party integrations. So you need to have ways to communicate with all these other services too. And Rust lets us solve all of these pretty well. Like low overhead, we don't have a GC to fight about with memory. As I said earlier, the performance is very explicit, right? If you write no clone, there is no allocation. You have very high failure tolerance because of this like exhaustive error checking that you get through ADT enums, like resultant option. You have very high performance. I already said that 2 times. Let me not repeat that again. You can have very predictable prioritization of work. Especially in async Rust, you can do things like manually scheduling when futures run, like essentially delegating less to the sort of scheduler in the like the async scheduler that you use, and instead saying, for example, I want to pull all of my already opened connections before I accept new connections. And we have a really, really strong ecosystem of robust crates that deal with user input, like Hyper, right? Hyper does not panic when you send it an invalid bit of HTTP. And certainly JSON does not panic if you send it like a quote too many. There's one thing that kind of sucks right now in Rust, though, which is the story around third-party integrations and like third-party SDKs. Like, if you want to talk to AWS, there's an SDK, which is good. Like AWS has put a lot of effort into this, and I'm very happy they have. But like, it does not retry S3 uploads correctly, for example. And these are things that you run into very quickly when you're developing at our scale in production. GCP just does not have a Rust SDK. They hired somebody a year ago, and I think, I don't know what happened to them. Like the repository just fell dormant in February, and I was kind of sad to see that. Azure has an in-development SDK, but it's not ready yet. Stripe doesn't have a first-party SDK, third-party only, and it like unfortunately takes a very long time to compile. Twilio, like their solution to using Rust is, here's an open API doc, and here's an open API code generator. Plug them together, right? Which is, yeah, not fun. And this problem gets even worse because the Rust ecosystem is not even very homogeneous for these sorts of applications, right? You can have synchronous HTTP servers, you can have servers that use Tokio and OpenSSL, or Tokio and Rust TLS, or async std. And all of these, if you're using, for example, Tokio and Rust TLS, you need to make sure you use a library that doesn't use Tokio plus OpenSSL, because otherwise you're bundling 2 different TLS libraries into your service. So finding a library that implements the API that you need doesn't even mean that you can use it. So this is like quite a challenge still in the ecosystem. And our experience with this is that you end up building a lot of little mini SDKs. So internally we have SDKs. I call them SDKs. They're really just like a bunch of types and like request calls with like retry handling for cloud storage, for IAM, for secrets manager, for instance metadata, for like Postmark to send emails, NPM to fetch things from the JavaScript registry, talking to Let's Encrypt. Like Let's Encrypt was, yeah, we were so happy with our sort of mini SDK. We had to like implement all of it. So that one's open source. And then, yeah, GitHub, there's a good one called, I think, Octocrab, but it unfortunately doesn't implement half of the things we need. So had to roll our own there too. I'm probably missing a bunch, but yeah. And this sort of points to a different problem, which is that hurdles, in our experience, appear at the extremes. Like we have internal repositories that build 14 different binaries from a single cargo workspace that have 25 different test binaries. And this has challenges, right? Like I have a very powerful Linux machine at home, and building this in parallel requires upwards of 40 gigabytes of RAM for like a one-line change, 40 gigs of RAM. And that's like a really high bar for somebody to like contribute to this project now, right? You can't do this on an M1 Mac. Like if you have 32 gigs of RAM, you're just out of luck. Cargo test doesn't have sharding support out of the box, right? Like you can't build your cargo test binaries on one machine, then move them to another machine and execute them there all with cargo test. You can do it if you have sort of your own little test runner, which I'll talk about more in a second, but yeah, these are things you have to build yourself. There's no machine-readable JUnit output for a cargo test, which is at a team or scale. It's like flaky tests are a thing, and you need to be able to know that they're a thing, and you need to have a graph that shows you this is our flaky tests today. And if you can't get machine-readable output out of your test runner, like, do you just have somebody that goes through your CI logs and like writes them down in a spreadsheet? Like, no, you don't. Yeah, so effective CI caching, also very difficult right now, especially for large workspaces. If you have a single workspace, it's pretty good actually. But like all of the sort of popular caching systems for GitHub Actions, for example, don't cache binaries in a workspace. They essentially exclude those from a workspace, which means that if you have a workspace that has 14 binaries, you change one of them, you have to rebuild all 14. Not great. And then target directories. I'm sure some of you have very large target directories on your systems. We have this channel in Slack where everybody just posts their records on who has the biggest target directory, and they get very large. So yeah, there's hurdles that appear at the extremes, but it's fine. If you have a team that's large enough, you can deal with this. You just have to be aware of it. Like for example, we have a custom sort of wrapper around cargo test that lets us build test binaries on one machine, then package them up into a zip file, put them onto a couple other machines, and execute the tests in shards there, and then later combine all the results. And we can use the unstable message format JSON. Actually, I don't know if it's still unstable. Maybe it's stable at this point. To convert there's a JSON output for cargo test, and we have a system in place that lets us convert that to JUnit. So there's ways around it. You just have to be aware and have to build the infrastructure. So what's the conclusion here? Rust is really, really fantastic for building cloud services. Like, I absolutely love it. I would not use any other language, like never. It's great. The reliability is absolutely excellent. Like the amount of times that we debug production things where it's related to like some edge case we didn't deal with or related to panics, it's like, I don't know, once a month maybe. It's very rare. Fantastic built-in tooling. I alluded to that earlier. But we really need to get vendors to ship better SDKs. Like it's, obviously the ecosystem isn't as large as JavaScript, so vendors aren't going to spend as much time as building JavaScript or building Rust SDKs as they are doing JavaScript SDKs. But we need to sort of put in better systems and better like ways for vendors to say, or vendors that do want to build SDKs, they don't even have like one target to develop against, right? They have all of these different targets to develop against. It's not easy for them to do. We could do a much better job there. And yeah, if you are building Rust with a larger team, you have to be aware that a lot of the tooling in cargo is really great, but it runs up against some limits at scale, which is totally normal. This happens with every programming language, but you just have to be prepared for it, right? And you have to be aware that you're going to be at the forefront of sort of innovating on tooling. So yeah, that's that. I also want to mention we're hiring. So if any of this seemed interesting to you, we're 100% Rust shop, fully remote. We have like 300,000 monthly active users, do a bunch of open source. Please talk to me in person. I would love to talk to you. Yeah, thanks. This is the website. If you want to check it out.
Questions? Yep.
I'm curious. So you seem to build like most of your backend services with Rust, but are you also using Deno for some services to dog food it?
Yeah, no, we definitely do. Like our website is built in Deno, but it's powered by Deno, but the Deno is written on Rust, right? But yeah, like except we don't build any of our sort of foundational infrastructure in JavaScript because like you just can't, like JavaScript can't host itself, right? You can't build a cloud service that runs JavaScript in JavaScript. Well, I guess you could, but it's like this throws all optimization out the window.
Thank you.
Very interesting talk, thank you. Going back to one of your last slides when you were mentioning limitations in the test runner tooling, which are definitely there. I have two questions. There's another test runner in Rust, right? Which is Cargo Next Test,
yeah.
which does solve some of the hurdles that you mentioned. So number one question is, why aren't you using that? And the second one is, have you tried contributing your JUnit output to upstream, and what has been the response?
Yeah, so let me answer the first one first. We did actually try next test, but the problem with next test was that it changed too many other related things, right? Like the way it runs its tests changed, like there was too many other unrelated changes to the way it runs tests that would cause our test suite to fail, and we just didn't have the time, the sort of availability at the time to.
Is this due to the fact that it doesn't create separate binaries for every test? Okay.
Yeah, like one specific example I can mention is like we spawn a lot of sub-processes which need to allocate ports, and if you start 2 tests at once and they try to start on the same port, one of them is going to fail. So you have to have some sort of system in place that can sort of mutex lock a port, assign it to one process, and in some cases this is really easy. You can just tell the kernel, give me a port, because you like you listen on port 0, but some services don't allow you to do this. They don't plummet through all the way. So in some cases you just have to manually assign a port. And the way we do this now is that we sort of have a global mutex in our tests where all the tests can go grab a port from, and that's fine, right? And if next test then goes and runs all the tests in parallel in different processes, this doesn't work anymore. So there's things like that which, they're solvable, but just requires a bunch of work. And this was the easier approach. And then on the JUnit thing, so actually our JUnit sort of thing is not written in Rust. It's written, it takes the JSON output, pipes it through a Deno script, and then the Deno script gives you XML back. And yeah, I'm sure we could upstream it, but again, time pressure, and we didn't really have the time to do it yet.
Sure.
Hi, great talk, thanks. First of all, a question about an implementation detail, just to understand. You call your isolates because they are the V8 isolates underneath?
Roughly, yes. Yeah.
Okay. And when you were speaking about high density, how do you actually measure resource usage or anticipate resource usage to allocate, let's say, workload on nodes inside isolates? Because what I do usually in Kubernetes is I test, and then I know what amount of milli CPUs a workload uses, and then I request that amount so that the Kubernetes scheduler can actually allocate that. But since you run code provided by customers, how do you do that?
Yeah, that's a great question. There's a lot of this stems from the fact that we have the ability to, even though we share resources, isolate tenants in such a way that if there's a single tenant that comes and wants to use a bunch of resources, we're going to throttle that single tenant before we throttle everyone else on the platform. And this allows us to sort of have a global utilization target that we target, and we like scale up our underlying infrastructure to meet that target. And if there's a single tenant that decides that they need a lot of resources and we just don't have those resources available right now, we'll throttle that individual tenant rather than everyone else. So this, yeah, we sort of do a similar thing where we measure, but we don't measure on a single tenant or a single service, but we measure sort of the entire system, and we know like what utilization percentage results in good scaling behavior for us.
Which, correct me if I'm wrong, could mean that a tenant that has a compute-intensive task that would need a full CPU to run at a high throughput could run at a lower throughput because it is sharing resources with other tenants.
Sometimes. So this is, yeah, so we have like multiple different compute products. Like one of them, for example, is queues, where you enqueue tasks and then we pop them off the queue as we have availability to process them. And then you have things where you like synchronously process requests. And the synchronous request processing, for example, has a CPU time limit where for every request you cannot use more than a certain amount of CPU time. So if you want to do some async background work, to put it into a queue first and have the queue processor pick it up, because that has like more control over when it has sort of resources available. And then the other thing is we are deployed in many, many regions, right? And even if we don't have space to run the code in the specific region that's closest to you, we can always fall back to a region that's slightly further away that still does have space. So like it needs like a very, very large spike for us for the system to be like completely unable to process your request.
Perfect, thanks a lot.
You're welcome. I feel like I've already gotten a question from you, but
Sorry?
I feel like I've already gotten a question.
Yeah, that's the second one. I'm curious how native dependencies work in Deno. So could I use maybe Skia or my own Rust code from a Deno script?
Yeah, you can. So in sort of, in the isolates, it cannot be native code. It has to be compiled to WASM. But Skia, for example, can be compiled to WASM, and Rust code can also be compiled to WASM. In the Deno CLI, we also have an FFI system that lets you expose or call into native code through an FFI interface that's like CABI compliant.
Awesome.
Hi. I don't know if you already covered this, but you mentioned, for example, having OpenSSL shared between multiple tenants. It's not really the topic that you've been covering, but like, have you put any significant thought into the security implications of something like that? If, for example, one tenant puts OpenSSL into an undefined or security vulnerable state, then another tenant may themselves become vulnerable, right?
So the things that we share are code pages that are entirely read-only, that can never be modified. So we would not forever share like runtime sort of internal state of OpenSSL, for example. And actually, we don't use OpenSSL, so it was a bad example in the first place. But the way you can, I know, RustTLS is great, except, well, okay, I'm not going to get into the except, but I have many experiences from RustTLS in production. Like things, for example, V8 has a read-only heap, which is sort of like strings, for example, that are just part of the JavaScript language that are shared across all runtimes. Like, I don't know, the string window is something that's very intrinsic to JavaScript, or the string toString, right, is another string that's very intrinsic to JavaScript. And those kinds of things can be put into memory pages that can be shared across all runtimes because they're really just read-only. And there is actually another concern related to the page sharing, which is ASLR, address-based layout randomization, and I could get into that too now, but that gets like slightly too complicated. But yeah, there's definitely considerations you have to take when you're doing this.
Thanks.
Have you put some specific measures to mitigate timing attacks like Spectre-like, or are you relying on V8 and its measures?
So we practice like a security system that's very onion-like. We don't rely on a single layer of security for any of our security measures. I think everybody should do this, right? So no, we don't rely on just V8 to do isolation. We also have other sandbox layers in place. And we, for example, take very specific care to avoid timing side channel attacks by not exposing any high resolution timers. So we don't, in HTTP handlers, for example, you cannot do any multi-threading. JavaScript is inherently a single-threaded language, so there's no way for you to share memory between two threads, which means you can't construct a timer in userland. And if there's no high-res timers present and you have sufficient protections on your I/O, there's no way you can get enough timing information to build timing side channel attacks. So there's sort of measures in place that we have for that specifically, and then other sort of security layers like isolation provided by Linux and things like that.
Thanks.
Any more questions? Hands? Yep. I knew that.
I was wondering about you showed the hypervisor on Deno. Is it on which level is the hypervisor sitting? And like, can
you repeat the question?
Yes, on the hypervisor portion of things. Can you explain a bit more how it looks like and how it operates on which layer of the onions of hardware near?
Yeah. So the hypervisor. Okay, so let me see, what layer should I dive into this? So we have the actual isolates that execute code. Around these are various other sandboxes, and around those sandboxes is the hypervisor that manages when the sandboxes are created and destroyed. But all of this, including the hypervisor, sits inside of another sandbox that, for example, prevents accessing our internal networks or accessing sensitive secrets or accessing our database or like various other things, right? So there's layers that are inside the hypervisor that isolate one tenant from each other, and then there's layers outside of the hypervisor that isolate the hypervisor from everything else. And this means, for example, that our hypervisor itself is completely untrusted. We do not trust our hypervisor, which sounds kind of weird, but like the hypervisor does not get any permissions to do anything by default. Like if the hypervisor wants to request a file from our file storage service, you can have static files on Deno Deploy, for example, then with an incoming request, we grant you a permission that you can pass that permission token later to a different service and get that access. But the hypervisor itself cannot like grant access or anything, which also means that if you have a tenant, like, yeah, we effectively do a lot of things to sort of minimize the possibilities of vulnerability or of exploits at various different layers. Yeah, including at the hypervisor, under the hypervisor, above the hypervisor. Yeah.
Anyone?
Oh, here. Behind you.
So you've shown that Demo can basically run JavaScript code as isolates, but you also mentioned WebAssembly a few times.
Yeah.
Can you use those interchangeably? Like, can you just write an isolate completely in Rust then and compile to Rust in form of WebAssembly?
Yeah, no, we support both interchangeably. We support the WebAssembly API that's available in the browser. So actually, I can show you this. We have new WebAssembly dot instance, or I think it's instance. You can instantiate a new WebAssembly instance and use it the same way that you would WebAssembly from the browser. Which has the really nice benefit that like all your tooling, like emscript and WASM bindgen, all that kind of stuff just works because it already outputs this browser yeah, it already outputs WASM that assumes that a browser is there to execute it.
Okay, thanks.
Nice talk. Do you rely on unstable features in Rust?
No.
Could you rely on unstable features that would help you?
We do not rely on unstable features, and we have not relied on unstable features, and we are not planning to rely on unstable features. With the exception of, I don't remember if this message format thing is unstable. If it is unstable, then we use unstable specifically for that and for nothing else. But other than that, like all of our crates are published, sort of the foundational crates that build up Deno, the CLI, are all published to crates.io, which means we also don't have any dependencies that are not published to crates.io, and you can just run cargo install Deno. And this builds in stable Rust.
Try? All right. Thanks for the talk. What's the number one thing, new thing for you that you learned while developing and contributing to Deno and trying to integrate, with isolate processes from V8, additional tooling maybe around WebAssembly, etc., or all these security checks for the hypervisor, etc.?
Yeah. I don't know, there's a lot of things I learned. Like when I started at Deno, I had very little understanding of how sort of, how the Linux kernel deals with security, especially I was not aware of how seccomp worked and like other things like this. I think I gained like an appreciation for very robust error handling. In the beginning, I was very happy to use an anyhow for many things, and we still do use anyhow for things. But yeah, as time went on, I realized like having really structured errors is something that's super, super valuable. What else? I also learned to appreciate the build times that Go has. They sort of, I came before this from a dynamic language, then I switched to Go. They were both very fast in sort of compile times, and then I came to Rust. Yeah.
Thank you.
Also, like not 250 gig target folders is kind of a great feature.
Okay, we can have one last question if you got it.
So you showed us the feature with the key value store. Is this only in the cloud service or also when you run locally?
No, this also exists when you run locally. Actually, why don't I copy the code, paste it here, Deno run. It's going to allow all access. I wrote this code, I trust it. Oh. It's kind of cheating. And it works, see. The reason it's incrementing twice is because Chrome's also sending a favicon request for every thing here, so yeah. It's back. So one of the interesting things is actually that some of our sort of built-in APIs are backed by different primitives in the cloud versus locally. So locally, Deno KV is backed by, there's multiple backends, but one of them is SQLite. This is the default backend. And then you can run this SQLite server on your own VPS and connect to it. But if you're running on Deno Deploy, you're actually using a completely different globally distributed system that's under the hood, makes use of Foundation DB and our own sort of transaction processing system and replication system, which, yeah, it's kind of cool. We can abstract all these things away behind JavaScript APIs. Okay, thanks everyone.